Doc here for the Physics of Sound and Music. We're going to review the chapter on signal processing, which is Chapter O. So we'll go here to the text, call it up, and slide it over here, and see what we have. Chapter O. Well, Chapter O begins with filters here. Now, a filter lets through a given set of frequencies, a range. Think of it like a birthday party where this here says if you are less than 20 years old, you can come to the party. If you're greater than 20, you cannot. So we have transmission 100% for the young ones and 0% for the high ones. So I replace frequency by age in my analogy. Here we have a black box. Does the job. We'll look at that later, see what's in there, the electronics. But for now, this is simply a box that represents the circuit for the low-pass filter. Here you can imagine the wiggling going on here. You're pushing a current in, pulling it back, and that's your way of thinking of a signal, simple signal sine wave, just wiggling back and forth like that and seeing what happens. And the rules apply to sine waves. That's very important to note that these filters, how they work, you think of sine waves coming in, and this gives you the percentage coming out. So if you have a low frequency sine wave here, you're in 100%, you come out, and if you have a high, you do not. So what happens if we move on to looking at the way to handle a group of sine waves? See, here I'm going to look at a rant wave coming in, and a rant wave, here's your Fourier spectrum. You have, for a 50 hertz rant wave, you have 1 full cup of the fundamental. You then have 1/2 a cup of the second harmonic. The fundamental is your first harmonic. 1/3 of a cup of the third harmonic, and 1/4. Remember the way the harmonics go. If your fundamental, your first harmonic is 50, your second one is double, 100, your third one is triple, 150, or you can think of this as simply adding 50 at each stage. That does the job too. Then you get, for this low-pass filter, anything less than 275 goes through. Think of that like a window. There's a window there. So here the first 5 harmonics go through, and all the other harmonics get filtered out. It's very, very important when you analyze a filter, you break the wave that you have down into its sine wave components using the Fourier analysis that we did earlier in our course. And then you're ready to go. If we move on to the high-pass filter, this lets through anything that's greater than a certain value. This is called the cutoff frequency in each case, the cutoff, and here we let things go beyond the cutoff. So if you had our age analogy here, senior citizens, college for seniors that we have on campus here, used to have an age limit. Now they let anyone in, but let's pretend they have an age limit, and if they do, say 65, then you would have everyone over 65 at those classes, and here no one that's younger than that. Here's our black box again for the high-pass filter. We'll get to the electronics in a second, and as we wiggle away here, the high frequencies get through, the low frequencies get wasted or get absorbed. So for our rant wave, for the high-pass filter, anything greater than 275, so your 300 gets through all these upper harmonics. This changes the timbre of the sound. See? And we move on here to the bandpass filter. For a bandpass filter, think of it as having 2 rules. If you're greater than 20 years old, you're in, and if you're less than 30, you're in, and the overlap would be this region here. And the way we're going to give those instructions, we'll say if you're 25, if you're in the middle, and you're plus or minus 5 on either way. So they add across here and get 10 years. So if you go from 20 to 30, it's 10 years. That's your bandwidth. And your center is the one right in the middle, which in this case is the 275 we had earlier. And I'm going to go 100 on either side, so my bandwidth is 200 hertz. I go from 175 to 375, and that means all of the harmonics that are in between there get to go through, and that would be here the 200 is greater than 175. So the 200 is in, and you go up to 350, and then 375, see, is there. So you get those four. Notice that you get the relative heights, since this is an ideal filter where it's all or nothing. You get 0 or you get everything. Real filters in life will have some like 80% or 70%. They will not have this sharp cutoff like this. Kind of go up like a mountain and like that. So in some region there, you'll get some various percentages, but we're doing an ideal filter here. So that simplifies things in our analysis. If we look at what's inside the circuits, we look at our RC circuit. Here's our resistor, here's capacitor. If you have the battery this way, you charge up the capacitor, where you have plus on top, minus on the bottom. Electrons actually do the moving in circuits, but electrical engineers just think of the plus going this way. And then if you have it the other way, you charge capacitor up that way. Well, an alternating current switches back and forth, and that's a signal. And if we go at a high enough frequency, over 20 hertz, then when you get that signal through a speaker, we can hear it. So here we're wiggling around, and I have an analogy to help you understand the physics. Say you have a constricted hallway, because the resistor means it makes it hard for current to travel. And here you have a cafeteria, C for cafeteria, and we're going to fill that cafeteria up and have different shifts for eating. So here, if we have a low frequency, the cafeteria gets a chance to fill up. Let's say every 2 hours, you see, you're pushing folks in and then you're pulling them back like that. So there's action here. So low frequency action is seen here. If you go to high frequency, where you're going like this, where you say, hey, go eat, but then 10 minutes later you're pulling them back, they never really get the chance to fill up the cafeteria and eat. But the current, see, moving back and forth here like that, V is IR, Ohm's law, you get action here. So you memorize low pass for the C, the cafeteria, and high pass action is seen here. Voltage fluctuations are seen here when you're wiggling back and forth at a high frequency, and the voltage fluctuations are seen here more when you go at a low frequency and give that capacitor a chance to charge up. So we have here our simple two-way speaker system, where you tap off the low frequencies here and the high frequencies there. Once I took away an inexpensive record player, and that's all I saw. I saw a resistor and a capacitor. Wow. And that's your two-way crossover network. So you cross over, in other words, it's saying the high frequencies are crossing over to come out here, and you put a small speaker there, a short wavelength, small size, to specialize in that, the tweeter. And here you farm out the low frequencies to a bigger speaker that can support bigger wavelengths and bass, woof woof, and that's the woofer. So we know what's inside now in a simple circuit. And for the diagram, I like to read from left to right. So for the low pass, I'm going to bend this wire down so I can see the capacitor here as the output, reading from left to right. Simply bent the R down. And for this diagram, I'm going to bend the C up. So in other words, if I bend this up, then it's on the bottom here. Then I come in and see the outputs cross R, but I don't like the C being down there, so then I turn it upside down. So doing that, we get this filter here, and this is inside the black box. We now know the physics, what's going on with these two filters. And I've made these ideal. This will not be ideal. This will actually have a little hill coming down and a little hill going up. So we come to the bandpass filter, which is simply putting two of these together. You have two rules. Say if you're less than 40, or here if you're greater than 20, the overlap gets the job done. So we have to pick different values so that we have different filters here. If these filters happen to be the same cutoff, then you get nothing, because you want to have an overlap. So you want this one to be farther to the right than this one's more to the left, so there's a region in the middle. So I put these subscripts there. That's the bandpass filter, and we simply stick two of these together. Here is your low pass filter, because you have the capacitor there on the output, and then that goes into the high pass filter, and because there's overlap, you get the bandpass filter. An equalizer is nothing more than a series of these, but in the old days, I remember not having much control over filters, just having two controls, a bass and a treble control in the stereo system at the house. So here you have a filter, low-pass filter, that has an amplifier. Remember from our previous chapter, amplifier is a transistor where you have a little bit going in the back door, and that little bit there, when it goes on, makes this transistor activated, and then when you wiggle here, you get bigger wiggles from top to bottom. This is a resistor that I can control so that I can vary how much current is swishing back and forth here, and then I tap off there, and that's my bass. Here's my high pass filter. I tap off there, I get my treble. So when you go to the band pass filter, you simply put the band pass filter into the amplifier. So we just simply tack on the amplifier. This is a way to show that there's a ground and a plus, so I don't have to show the battery there, and it's easier to see. But this one here is showing you, the battery. Alright, so then we come to the equalizer, which is a series of bandpass filters with these centers, and this lets you control the entire spectrum. So you just have these here. We have one of those here, one there, one there, one there with different characteristics. You have the left channel and the right channel, and you can control them. This is the overall amplifier here, the overall loudness, and then you can control these. Notice that they double the frequencies here so they can span the hearing. That's a principle in our course, the doubling of frequencies. That's how the ear compresses and can hear so many frequencies in the cochlea. All right, so what about Dolby? Well, Dolby is for the tape. When you have tape, the old days having tape, you get a hiss when you play back. Those baby little dipoles, those little baby magnets on the tape, don't behave themselves at room temperature, and you get this hiss when you play back. So this hiss is over 5,000 hertz, 5 kilohertz. That's where you get the hiss, and that's annoying when you play that back. In fact, in the old days with cassettes, my dad would say that, hey, you can't tape music with cassette, only lectures, like college lectures or something, because you get that hiss in the background, you can't enjoy the music. And Mr. Dolby here comes along and says, we'll handle that. Since it's only on playback, we'll have a filter when we tape it. We'll tape the sound for the high frequencies more, overdo it, and then when we play it back, we'll put the Dolby playback filter in, which reduces the high frequencies, but since you already taped them too loud, you bring them back to normal, but then the hiss gets punished. See, that's the whole idea. Since the hiss only comes about on playback, tape with the higher frequencies louder and then playback lower, and then you get the same straight line here. Basically here you get the same thing for the music, but then the noise, which has that hiss, gets punished and goes down. That's the Dolby system. Another system that was used here, the DBX compounder, this has to do with the tape's inability to get 100 decibels. Now decibels here, drop of a pin, 0 decibels, and here blaring orchestra, 100 decibels. The tape just can't handle that. It gets it gets saturated. Can't do it. Tape can only handle 50 decibels. So they take the decibel level here, divide by 2, and that's compression. Electronics, it compresses it, tape it there, and then when you play it back, you expand it. Now, neat thing about that is that noise that comes in that's low gets punished and goes down this way, and that is also nice for handling the noise. So here you have it. In our course, we've done a lot of stuff. We've done microphones, and we have done amplifiers. Here's your microphone. Here's your amplifier. This is a review of past things, and here is your speaker, all the physics shown, and here is your record player, which runs on those hills and wiggles, and that's the Faraday's law going on there. See here, when you talk, you get this wiggling going on, and that's the Faraday's law. You get the electricity. When you have motion first and current second, that's your Faraday. Here, if you have, in this case, current first and then motion, that's amperes, like you're making an electromagnet. You're making a magnetic field in there, and that responds. So here you have Faraday's law, left and right channels as these things wiggle, and here's your resonance circuit, which we did, the radio, the inductor here, the resistor, and the capacitor. This is a little dial there to let the plates change their area that they're across from each other. Just take your hands, for example, put your hands up, and then rotate the hands, say, with an inch apart or so, and then rotate one hand away. You'll see that your hand, the area there, with like the two plates, then varies when you have them there. That's how you can tune in different radio stations. And here we have added. See down at the bottom here, we have our this is our magnetic tape here going on, where you tape or you can make a recording, and this is here your equalizer. So that takes care of signal processing.